Alright guys, I'm going to take some time and go over each of the examples from your class notes packet. Okay, I'm just going to go over the ones that we didn't have time to go over in class. I'll finish up one that we actually started, but I'm going to just go ahead and go through each of them and make sure that we're okay and that we understand each of them, because you're going to have homework problems that are similar to these, or just as review. So let's start with this one. This is the example number 4 from your packet, which is a battery with an EMF of 12, internal resistance of 0.05 ohms. Okay, it's then connected to a load resistance of 3 ohms. The load resistance is just the resistance that's on the outside. Okay, so let's go ahead and look at that. Essentially, we then have a circuit that looks like this one. You have the EMF right here, which is 12 volts. You have the internal resistance, which is inside your battery, right? That's why you have this reddish circle, because that's your resistance inside, so that's 0.05 ohms. And then we have the load resistance, which is going to be 3 ohms. Obviously, that's going to be a lot greater. That's the point. It wouldn't do us any good to have a battery that had an internal resistance much bigger than what we were eventually going to get out of it. So here we go. Let's go ahead and work this out. First, we're going to find the current in the circuit. Okay, so in order to find the current in the circuit, we know that the total potential difference of the circuit will equal the total current of the circuit times the total resistance of the circuit. Now you note that these resistors can be treated as if they're in series. And so when resistors are in series, we can just add them together. So the potential difference of the full circuit is 12 volts equals I times the resistance, which would then be 3.05. And so once we calculate that, we just go 12 divided by 3.05, and we get our answer of 3.93 amps. Okay, so the current is then 3.93 amps. Now the second question is, what is the terminal voltage of the battery? Okay, well, if I have a current of 3.93 amps, the terminal voltage is the difference between the positive and negative terminals, right? So I know I've got 12, but I'm going to lose some of that due to the internal resistance. So let's find out how much we lose due to the internal resistance. So if we do that, this is going to be the voltage of the internal resistance, which is then going to be equal to the current times the resistance. So 3.93 times 0.05, because I'm just looking for the voltage loss there. So here we go, 3.93 times 0.05, and we get 0.1965. So that's the internal potential difference, is 0.19. It was about 0.20, right? Okay, so if that's the internal, the question is, what is the terminal voltage? So what are we actually getting out? Well, we're getting out 12 minus 0.2, which is then going to give us about 11.8 volts. Okay, so that's our terminal voltage. Let's go on to letter B. Letter B says calculate the power dissipated in the load resistance of the battery and the power delivered by the battery. Okay, so let's go ahead and look at each of those. First, let's look at the power dissipated in the load resistance. So that's going to be power equals, now we know that power is equal to IV, right? But using this idea of V equals IR, we can also rewrite the power is equal to I squared R, right? Because V equals IR, so if we put that in for V, we get I squared and then R. So we can then find the power, which is equal to the current, 3.93 squared, times the resistance of the load. And so then we get a power of 3.93 squared times the resistance of 3, and we get 46.3 watts. Okay, and now the second part of the question is, what is the power delivered by the battery? Okay, so if we want the power delivered by the battery, you can do it a couple of different ways, but if you want to know how much is then being delivered, you can find the total amount from the voltage, right? On the answer sheet, I actually only found the power lost in the resistor, right? And so you can go ahead and work it out any way that you want. The power of the resistor, of the internal resistance, of course, is going to be equal to that 3.93 squared times the 0.05, which is going to give you what's in your answer key, which is 0.772 watts. So that's the power lost in the resistor. And so the total amount from the battery would then be these two added together, right? Or you could have just used the initial voltage and been able to figure it out that way as well. All right, so that's example number 4. Let's go on to example number 5. This is now dealing with capacitors in series, right? So now we talked about in class that when we're finding the equivalent capacitance of a circuit in series, that we're going to add up the inverses. Okay, so for letter A, 1 over the total capacitance is going to equal 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3. And so that means it's going to be 1 over 12. Now I'm going to just use units of microfarads, so plus 1 over 6 plus 1 over 4, but just make sure you recognize that it's microfarads. So we'll go 1 over 12 plus 1 over 6 plus 1 over 4. And then you want to do 1 over that, right? And so now we'll go 1 divided by that, and we get a total capacitance, or an equivalent capacitance, of 2. So capacitance total is going to be 2 microfarads, right? Because I'm working in microfarads. All right, so there's part A. Let's go on to part B. Okay, so there's B. We're going to do the charge drawn from the battery. So the charge should be fairly straightforward because we know that capacitance is equal to the charge divided by the voltage. And so since we know that the potential difference of the battery is, in this case, the EMF 8 volts, then we can say, well, that means 2 microfarads equals the charge over those 8 volts potential difference. So we go 2 times 10 to the negative 6th times 8, and we get 1.6 times 10 to the negative 5th, which if we put that in terms of microcoulombs would then be 16 microcoulombs. So Q equals 16 microcoulombs. All right, let's go on to letter C, the charge on each capacitor. Now we talked about in class how if I get a certain amount of charge moving to one capacitor or the other, that means that I'm going to have the same charge here and there. Right? Okay, we got positive and negative, so I'm going to have the same charge there, and the same charge there, and the same charge there, right? And so I'm going to end up with the same charges, okay? And so therefore, sorry, this is going to be plus minus, and plus minus. So each capacitor will then also have 16 microcoulombs, right? Each one has to have the same charge. Okay, let's look at D. Letter D, the energy supplied by the battery in charging the capacitors. Okay, well, if you think about our batteries, the capacitor we learned before, the energy of a capacitor is equal to 1/2 QV. All right, now, since I'm looking for the energy supplied by the battery, then I would have to then look at the charge and the voltage of the battery, or I can look at the whole circuit, right? There's lots of different ways you can look at it, but let's go ahead and just work this out. So 1/2 times the charge, which is 16 times 10 to the negative 6th, and then times the voltage of the battery, which is 8. And so we should get 0.5 times 16 e to the negative 6th times 8, and we get then 6.4 times 10 to the negative 5th, which is then 64 microjoules, right? Move the decimal one place, so I get 64 instead of 6.4 to the negative 5th. All right, so that's letter D. Easy enough, right? Let's go on to letter E, the energy stored in each capacitor. Well, each capacitor then, right, is going to have the same charge, but they're going to have a different voltage, right? So there's a couple of ways that you can go about this. Probably the easiest way is if we take that energy, right, which we know is 1/2 QV for a capacitor, and then we say, well, for a capacitor we know that the capacitance equals Q over V, which if we rearrange that means that the voltage equals Q over C, right, multiplied by V divided by C. Then I can now take this and plug it in there, and so I'll get the energy is equal to 1/2 Q times Q, so Q squared over C. Alright, now this is not given to you on the AP exam, but you can figure it out fairly easily with the different ones that you have. Otherwise, you're going to have to go through and solve for the potential difference across each of the capacitors. Recognize that each one is going to be different, but if you add them all together, you're going to get that potential difference of 8 for the battery, right? So let's go ahead and do this. We can do it for each one. So energy will be, for the first one, will be 1/2 times 16 microfarads squared, or sorry, microcoulombs, right? That was our charge, divided by the capacitance of the first one, so let's go 12 microfarads. So let's go ahead and move this over. We'll go 0.5 times 16 times 10 to the negative 6 squared, and then divided by 12 times 10 to the negative 6th, and we'll get, I didn't need that. We'll get essentially, right, this is then 10.6 times 10 to the negative 6, right? It was to the negative 5th, so I move the decimal place over once and get negative 6, and so that will be microjoules. And then I can do the same thing for the 6 microfarad and the 4 microfarad. So let's just go in and change the 12 to a 6. And so for that one, we'll get 21 times 10 to the negative 6, 21.3. So for the next one is 21.3 microjoules. Sorry, I don't need the negative 6 if I have the microjoules there, right? And then for the last one, we'll go ahead and do it again, but this time for the 4 microfarad one. And so 32. So 32 microjoules. Alright, there you go. It's been about 10 minutes. We've gotten through 2 of them. Let's go on to the next one. Alright, here we go. Example number 6. Alright, this time we've got capacitors in parallel. Alright, now parallel, remember, that means that the voltage is going to have to be the same across here as it is across there, which means we're going to have the same potential difference for all of them. Okay. Secondly, remember that the current and therefore the charge is going to have to split up between the 3. Alright, so let's go with letter A, the equivalent capacitance of the circuit. So remember, when they're in parallel, we just get to add them together. You should remember this from your AP equation sheet, equals the capacitance in parallel, and so we just get to add them all together. So 5 plus 7 plus 3 would then be 15 microfarads. That's letter A. Letter B, the charge drawn from the battery. So again, the capacitance will equal the charge over the voltage. We know the total capacitance is 15 microfarads. The potential difference is 30. So just go 15 times 10 to the negative 6th, and then multiply that by 30, and we get 4.5 times 10 to the negative 4th, or if I move the decimal over twice, that would be 450 times 10 to the negative 6th. That's what we're going to say. We're going to say 450, then we just solved for the charge. So 450 microcoulombs. Alright, off to letter C, the charge on each capacitor. Now remember here, the charge is going to have to split up, right? And so when we're looking for the charge on each capacitor, we're actually going to have to solve for each one individually, because the charge is then going to split up and go to this one or that one or that one. So we're going to use our equation from before, where we can say that the charge is, the capacitance is equal to the charge over the potential difference. The potential difference will be the same for each one, right? That's what we said in the beginning, is that if this has a potential of 30, then as I go around right here, that has to be a potential difference of 30 as well. And so each capacitor will have a potential difference of 30, take its capacitance, and then we should be able to solve for the charge. So let's go ahead and do that. For C1, it's going to be 5 microfarads is equal to the charge divided by 30. And so multiply, and we'll get 150 volts times farads will give me 150 microcoulombs. Right? Okay, let's go on to the next one. So that was Q1. Okay, for Q2, it will be 7 microfarads is equal to Q over 30. So multiply those, we get 210 microcoulombs. And then for Q3, right, again, capacitance, so 3 microfarads is equal to the charge over the voltage. So multiply, we get 90 microcoulombs is Q3. Alright, so now we found the charge on each one. Letter D, the energy supplied by the battery. Okay, so for the energy, we're going to do energy of capacitor, or energy supplied would have to be the same energy that's here, right? The total energy of our capacitor is going to add up to be the same amount of energy that we're putting out. So let's just find the energy of the capacitor, right? So the energy of the capacitor then is 1/2 times, now it gives us two equations. We can either do QV or CV squared. So if I want to use the Q, I can just add up all of the charges, right? Maybe I'll do that just to show you that we can do both ways. Okay, 1/2 QV. So if I decide to do the capacitance times the voltage, then that'll be 1/2 times the total capacitance, which we solved in part A, which was 15 microfarads, right? So 15 microfarads times the voltage, which is 30 squared. Okay, so if I solve that, I get 0.5 times 15e to the negative 6 times 30 squared, and I get 0.00675. Okay, which I can turn that into, if I want to keep it in microjoules, I need to move the decimal 6 places, right? 1, 2, 3, 4, 5, 6, so 6,750. If I want to be consistent with using those micros. Okay, or you could have done this. 1/2 times the total charge. Now we're going to have to add up all of those, right? 150 plus 90 is 240, plus 210 would then be 450 microcoulombs, then times the voltage, which is 30, and therefore we're going to get the same number, times 450 times 10 to the negative 6 times 30. Ta-da! Same answer, right? Very good. So we're going to get the same thing, 6,750 microjoules, and then last we're going to get letter E, the energy stored in each capacitor, and so we're going to do each of those individually, right? So we'll do the energy in capacitor 1, which would then be equal to 1/2, and then I would recommend using this equation, the 1/2 QV, because you already know the charge for that capacitor, and the potential obviously is still 30, and that way you don't have to worry about finding the actually you can do that one as well because we know the capacitance. So either way it's going to be fairly straightforward and easy. Let's just go ahead and do this. So 1/2 times the charge on the first capacitor, which is 150 microcoulombs, and then times the voltage of 30, so then 0.5 times 150 times 30, and we get 2250 for that one. Again, this is going to be in the microjoules, right, because it was microcoulombs. Okay, I multiplied by 150, so I didn't worry about the micros, so I need to keep that there. The energy of the capacitance 2 would then be 1/2 Q2, which was 210 times the voltage. So let's go ahead and change that to 210. So we get 3150 microjoules. And then the last one, 1/2 90 times 30. And then when we do that one, we get times 3, so I need to go by 10. So 1,350. Alright, so there you go. That'll match up with the answers that you have on your worksheet. Alright, I'm going to go ahead and stop the video so it doesn't go too long. And if you want to see the other examples, we have 2 more, then go ahead and watch the other video.